Today we are going to finish off some of the strategies for integration. I've decided to do a slightly different approach from yesterday, and I've just kind of taken a random snapshot of some of the questions from that section, and I'll talk through the strategies of why I would have chosen that one and how I would have approached the question. So at the side here is going to be the final, what you would do kind of thing. So let's focus on how I came up with this is the U sub, right? Well, I'm looking at this question and my brain would be saying things like, well, it's obviously got secants and tans in it. So I'm pretty sure it would be in that section. Remember the one where we did a trig integration? So I know it comes from there, and I'll be thinking to myself, well, the most likely things are going to be some trig identity or a U sub. And then I look at that and I thought, I wonder what U sub might work. And the first one that came to mind would be use the entire BOM. But I thought about that and I tried it out and I figured out pretty quickly that wouldn't secant square theta take away secant not play well with the top. And so what I did instead is I just chose secant theta. And when you do secant theta, can you trust me that this is what it becomes? And 1 over u squared minus u is much nicer looking than that. So I know I'm on the right track, but I'm still not finished. And then I say, oh, wait a minute, that can become 1 over u minus 1. Do you recognize that as the cover-up method? Right, that would be the kind of stuff we did 2 days ago. So when you're trying to solve these integrals, there's no guarantee it's just one thing fixes it. And this is a U sub followed by the cover-up method. This one here came out a lot easier than it looks, or maybe it doesn't look hard at all. But would you agree that there's really only one candidate? It typically isn't a U sub pretty much the guy to go for in this case. And the U sub I chose would have been 1 plus e to the x, because don't we have a rule, the guy inside the square root is the guy you should use. This one here is not so obvious. I could have chosen 1 plus the square root of x as my U sub. And if I did, I'd get into trouble later on, right? There'd be some bits left over that I'd have a really hard time fixing. And so I decided to do that U sub and it comes out nicer. Do you recognize this one as just a standard x sub with the horrible 49 generating a 7th? This one is a pretty standard integration by parts as long as you use f of x. This guy here, if you break it into the factors, doesn't it become a partial fraction question? Right, so that was yesterday's. And this one here, if you separate the sign and do a sine squared x in it, can you see that this becomes a U sub? So substitution, integration by parts, x subs, partial fractions, right? In that list, pretty much all of the above, there's at least one example of it. So I'm going to pick one and do the whole question, and then you can tell me which one of the ones that's left you'd like to see, and we'll call that done, okay? We could do all of them, but they would take far too long. So the one I'm going to pick is the ugliest looking one, I think, except I know something that you don't because I did it with my other class. This is an x sub. And the x sub that's going to work is 1/7 tan theta. Now, from our experience of x subs, don't they take forever and a day to do? They're like typically 15 minutes, but not this one. So if you differentiate with respect to theta, you get 1/7 secant theta tan theta. And if you do the crossover, the dx is 1/7 secant theta tan theta d theta. Now, The top dx gets replaced by all that stuff that I've just said a few seconds ago. The x gets replaced by 1/7 tan theta. And this guy becomes 49 times 1/7 tan theta all squared plus 1. And while I'm at it, why don't I cancel that 7th with that 7th and that tan with that tan? And so what we're now left with is a secant theta on the top. And this guy, when you square it, you get 49 times 1/49 tan squared, and that just becomes tan squared plus 1. What trig identity can you replace tan squared theta plus 1 with?
Secant squared.
And isn't the square root of secant squared just a secant? And do you see why this one came out a lot easier than you thought it was going to? Of course, isn't there still one job to be done? And that is to turn it into x's. Now, normally, wouldn't you be building a little right angle triangle and doing all that stuff? But in this case, I can bypass that because the only reason you build those right angle triangles is because your answer has sines and tans and secants in it. But this question only has a theta in it. So I'm going to do something a lot easier. I'm going to start off with this, but I'm not going to build any triangles. I'm just basically going to multiply both sides by 7. And that means that I can just do that to get there. So it's the inverse tangent of 7x plus c. So not every x sub needs all the steps. Would you agree this is a very special situation, but nonetheless, we didn't need to do anywhere near as much as we typically would do. So one more guy, and then we're going to move on. Any one of that list on the left that you may want to see? I would pick something unusual. I've never seen that kind of question done before. That would be my suggestion, but you pick what you like. Which one?
So it's like a one from the top. Anyone else?
That one or that one? Question 20 is the top and 21's below.
21.
Which 21? This one. 5, the square root of 1 plus e to the x. And it's a u sub. Would you agree it's a pretty standard u sub, isn't it? The guy inside the square root. That doesn't mean this is going to be an easy question, but at least that's pretty straightforward, right? That'd be the most likely thing to choose. Now, if you differentiate with respect to x, you get e to the x. You do the crossover, you get that. And 1 over e to the x times du gets you dx. And so we have 5, the square root of u, times 1 over e to the x du. That's not good. Agreed? But we have to turn the e to the x into something that's got u's in it, right? So where are we off to? How can I use this to figure out what e to the x is?
Would e to the x be u minus 1?
It would. So we now have that guy. And at first sight, it looks like that wasn't a very good use of. Would you agree that the new guy is even uglier looking than the guy we had? Agreed? Now, this is where the fun part starts. I am now going to do another U sub. I'm going to have to call it V sub, right? And this one is not 1 minus U, which is what you would expect it to be. What do you think it's going to be? This question kind of breaks every rule you're ever taught. It's a special case. Who's it going to be?
The square root of u?
Yes. Which I am going to call u to the half. When we differentiate it with respect to u, we get 1/2 u to the negative a half, which I am now going to call 1/2 u to the half. And when I do my crossover, 2u to the half times dv is equal to du. So I have square root 5v 2 u to the half dv over 1 minus u. Isn't u to the half v? So that guy, 2 times 2 gets me 10, and v, and he is also v, gets me v squared. And won't 1 minus u be 1 take away v squared dv? Are you okay with that? Would it help if I went and wrote that as 2v do v equals du? Right, does that help any? Right, now.
Is it supposed to be u minus 1 instead of 1 minus u?
U minus 1 instead of 1 minus u. And you are right. So we are now at this stage. This is stuff we have done this week. Didn't we do a question kind of sort of like that about yesterday? At the beginning of yesterday. Where do I go now? What do I do with 10v squared over v squared minus 1?
Minus 10 plus 10.
On the bottom, minus v minus 1, v plus 1. That's
No,
fine.
on the top.
Oh, what do you want to do on the tops?
Minus 10 plus 10.
Oh, yes. I like that. It's not the way I would have done it, but I like it because it's better than the way I would have done it. And that becomes 10 lots of v squared minus 1 over v squared minus 1 plus 10 over v squared minus 1. And you recognize this guy as 10? And do you recognize this guy as the cover-up method? And I think I'm going to stop there. Cover-up method works, but it just, you know. We did one question that looked horrible and took about 5 lines. And we took one question that looked relatively nice, wasn't much going on here. And didn't it take 3 shots and an integration by parts and a bit of weird algebra to get the answer? There is no guarantee that because a question looks nice or looks ugly, that it's actually going to be easy or hard to do. I mean, that one is deceptively ugly, you know, the method. Very messy. And we're finished. So let's tell you about what's not coming. And just in case you're curious, 7.6 is not in the syllabus. If you look it up, 7.6 is using tables to get integrals. And basically what that section would be is, if you wanted to find an integral, at the back of the textbook, there's something ridiculous like, don't quote me because I'm guessing, 300 integrals. And you find a guy that looks like your guy and you write the answer down. Right? Not really anything that you need to do. And you know, that's actually totally superseded now. In the real world, what you would do is you probably do Mathematica or something and just get it to do it. I mean, if you were practically going to do integrals, you don't normally do them by hand. You actually, once you know how to do them, you typically would let software or tables do it for you. So you might say, well, why do we bother doing it by hand? Well, if you know how to do it, isn't using tables or software just a shortcut to save you spending 20 minutes? I could do it myself, but it would take me 20 minutes, but I'll let the software do it. That's okay. But if I don't know how to integrate, I just know how to look up tables, then you really don't know anything, don't you? I mean, you could train a monkey to do it, right? That wouldn't be very, very intelligent. Analogy. I know how to multiply 5-digit numbers by other 5-digit numbers, right? I could do that by hand. Wouldn't I use a calculator if I had to do it? And I wouldn't think anything at all about doing that. Suppose I don't know how to multiply. Wouldn't it be a very dangerous world if I could only do multiplications by using buttons and pressing calculators, right? That's not a good foundation. So that's what 7.6 is about. 7.7 isn't going to be done either, because 7.7 has already been done. 7.7 is the Simpsons and trapezium rule that we did back in week 1. Why this textbook put it in 7.7 is ask the guy that wrote the book, right? But we've done it. It was included in those questions. So we never missed that. And so we're now going to do our 7.8, our last section in chapter 7. So once we do this guy, actually, well, pause a minute. Do you know that we pretty much know how to do every integration that you need to worry about? The techniques that you've got are pretty much all the major ones are done, right? So you know how to do U-subs, you know how to do integration by parts, power rule, X-subs, partial fractions, you know, all that kind of stuff, right? Done. 7.8 is going to be about what are called improper integrals. We're going to show you how to find integrals of a very special type. Unusual name, isn't that? Improper integrals. It sounds like there's something wrong, right? It's improper. Let's show you what they are. There are 2 types. Improper integrals of type 1 look like this. Do you notice that what they all have in common is that at least one of the 2 limits of integration is infinite of some kind? So if you have an integral where the guy up here is infinity, or the first guy is negative infinity, or it has both of them. We call them improper integrals of type 1, and you are going to find out next week how to do those. So let's look at type 2 then. What do type 2 improper integrals have in common with each other?
At some point, it'll divide by 0.
Right. So if you were visualizing them, wouldn't that be there's vertical asymptotes in them? This one, the vertical asymptote is at 1. In this case, it's at 4. And in this case, isn't it at 0? So if you have an integral and it has a vertical asymptote in it, so at some point you're going to have a number divided by 0, right? That's essentially what the guy that's going to cause the vertical asymptote. When that happens, you're looking at type 2, and we'll show you on Monday how to integrate those guys. So you might be thinking, what's he going to be doing for the next 20 odd minutes? We are going to do some skill building. Because to be able to do these, you need to know how to find limits. In the beginning of Calc 1, oh God, definitely week 1, but well into week 2 as well. Didn't you spend a lot of time finding limits of things? And we're going to look at that same situation. We're going to look at limits at infinity today, just those. So there are 2 main techniques that we are going to employ. And we are going to do a technique called brute force. And we're going to use a technique less common, but we will use it sometimes, which is called L'Hopital. Do you remember L'Hopital vaguely? Right. If you're not sure about brute force, it's what I call it when you make the thing infinite, right? You just plug in infinity and you do calculations. So let's focus on the first technique first, right? Brute force. Start off with a very simple case. We don't need that. Let's start again. It's limits I'm talking about. I'm calling them t instead of x because I want to. If you wanted to know the limit as t tends to infinity of 10 over t squared, brute force basically says replace the t by infinity, and then you do calculations with infinity. Now you have to be careful with infinity. There are certain things you're allowed to do and other things you're not. But would you agree that infinity squared is still infinity? That you're allowed to do. What number, and it is a number, do you get if you take 10 and you divide it by infinity? What number do you get? 0. So that would be the working that I would expect to see if you wanted to prove to me that the limit of t over t squared as t becomes infinite is 0. Now let's make it a little bit harder. Well, suppose I wanted to find the limit of that fraction. Most of these questions, by the way, end up being fractions. Well, I can't do brute force. If I tried brute force, don't I just get infinity divided by infinity? Right? And no, the answer isn't 1. Right? Infinity on the top divided by infinity on the bottom could be anything, right? So what we do instead is we do a little technique. It's still going to involve brute force at the end, but you divide the top and the bottom by, in this case, t squared. So you pick the highest power on the top's t squared and the highest power on the bottom is t squared. And where they're both the same, then it's easy. Divide the top and bottom by t squared. And when you do that, you change your limit into divide that by t squared, divide that by t squared, divide this guy by t squared, you get those guys. And then divide that by t squared, you get 3. And divide that by t squared, you get 3 over t. And this new guy, mathematically, is exactly the same as this guy, right? I've just rearranged how he looks. Now you do the brute force part. 4 take away 1 over infinity plus 1 over infinity squared. And 3 plus 3 over infinity. Isn't that 1 over infinity and that 1 over infinity squared? Aren't all those terms zeros? So what you're really left with is 4 over 3, and there's your answer. The limit is 4/3. In fact, what we really should say is it converges to 4/3, but the limit is 4/3, works fine. Do you remember doing guys like that? Still on fractions. Let's suppose I want to do the limit as t tends to infinity of 3t plus 1 over 4t cubed. I'll make that a t squared. 4t squared plus t. Yeah. Now I get the same problem as we had last time. I can't just do brute force right away because it doesn't work. What I can do instead is divide the top and bottom. And I just screwed up here. I apologize. I wanted that to be cubed. Right. So I have a t squared on the top and I have a t cubed on the bottom. When you have a choice between a square and a cube, pick the smaller of the two. Technically, you can pick either, but I find picking the smaller works better. So I get 3 plus 1 over t squared. And this guy gets me 4t plus 1 over t. And then I do the brute force. So 3 plus 1 over infinity squared, 4 lots of infinity plus 1 over infinity. Right, 1 over any version of infinity gets you 0. 4 times infinity gets you infinity, and 1 over infinity gets me 0. And so I now have this guy. And what does 3 over infinity get me? Right, so the symbol, it gets me a big fat 0. So that one converges to 0. For completeness sake, let's do the last version of how these things could tend to. So sometimes you get numbers like 4/3, sometimes you get 0. And lastly, you can sometimes get infinity, right? So let's suppose I had 5t to the 4 plus t squared. And I had 3t cubed, take away 2t plus 1 in the bottom. Now the choices I have, t to the 4 or t cubed, right? Highest power on the top is t to the 4, highest power on the bottom is t cubed. And my rule is when you have a choice, pick the smaller one of the two, in this case, t cubed. So that guy becomes 5t, and that guy becomes 1 over t. This guy becomes 3. This guy becomes 2 over t squared, and this guy becomes 1 over t cubed. And then we can do brute force. Excuse me. So 5 infinities plus 1 over infinity. 3, 2 over infinities, 1 over infinities. Excuse me. 5 times infinity is still infinite. 1 over infinity gets me 0. 3 take away 0 plus a 0. That becomes infinity and 3. And infinity divided by 3 is still infinity. And when the answer is infinity, we actually just say it diverges. Are you comfortable with this technique of finding limits by the brute force method, right? Plugging in infinity and see what it gets. Oh, by the way, we could have used L'Hopital in every single one of these questions. The reason why I chose not to is, do you know if you had to do L'Hopital with this one, you'd have to do it about 3 or 4 times before you got the answer, right? Because it wouldn't work the first time. Now, I want to hit you with some special cases, still brute force. This one caused a lot of trouble in my last class. There's nothing I can do except the brute force part, right? And the inverse tan of infinity is not infinity. It actually is a number. And if you think what number it is, you have to kind of turn the question on its head. What angle has a tan that's infinite? Because that's what the inverse tan does. It gives you the angle whose tan is infinity, right? So what angle has a tan that is infinite?
Pi halves?
And that is your answer. 90 degrees. Yeah, try in your calculator. Tan of 90 is infinite, right? Okay. Now, 2 more, and then we'll move on to L'Hopital. If I do the brute force technique, I'm basically doing that. If you sketch the sine function, doesn't it basically look like that forever? So what would the sine of infinity be? Maybe I should phrase it differently. Is the sine of infinity anything?
Is it 0?
I might say that's its average value, but not its limit value. The answer is that it diverges. Diverges just means it doesn't have a limit. Many times diverges is it doesn't have a limit because the answer is infinity, right? That's a different kind of diverge, but it still counts as a diverge. Would you agree that the sine function just goes up to 1, down to -1, but then it goes back up to 1 and down to -1? So if you traveled along the sine curve to destination infinity, would you agree that you wouldn't be stopping anywhere? You wouldn't be leveling off it anywhere. Wouldn't you still be continually varying? And therefore, if you don't have a limit, we say it diverges. Be careful with this last one. When you do the brute force on it, it looks like that. Now you might say, well, it's a cosine. Cosines go up and down. So do sines. So the answer diverges. No, not this time.
That looks like a cosine of 0.
It is. And what is the cosine of 0? What number is the cosine of 0?
Is it 1?
Yes. So can you see even trig functions can have limits? It just depends on what you do to them, right? Sometimes nothing, right? No limit diverges. Other times, yeah, it could be a number. Are we good so far? Still, you know, we aren't even going to go near integrating these guys. We're going to focus on just getting how to do limits, because once we know how to do limits, these questions are going to be a lot easier. Let's do the second stop. Do you know that the Invisible Man and Superwoman had a baby? Did you know that? The baby was nothing to look at. Nope, keep going. L'Hopital's rule says this: the limit as t tends to infinity, or any number, but we're just going to do the infinities today, of a fraction function, f of t over g of t, is the same answer as finding the limit as t tends to infinity of the ratio of their derivatives. And when you do L'Hopital's rule, it's a good idea to put a little capital L above the equals, and that tells people what you're doing. So that's essentially what L'Hopital's rule does. This allows us to find the limits of more complicated fractions. So let's do some practice at that. Let's suppose I wanted to find the limit of e to the 2t over t squared, right? If I plug in infinity, would you agree that you get infinity over infinity? So you can't do brute force, right? So we'll do L'Hopital. And L'Hopital says that you just differentiate the top and bottom separately. So t squared gets me that. And e to the 2t gets me e to the 2t times 2. Hopefully you remember the general. If you can, you should always cancel. So I'll cancel the 2's. And now I'm looking at that. But if I plug in infinity, I still have the z infinity over infinity problem. So I do it one more time. If I put my little L, differentiate e to the 2t, I get that. Differentiate that, I get that. And now I can do brute force. 2e to the 2 times infinity over 1. E to the infinity is infinity. Infinity over 1 is still infinity. So we would say that this one diverges. Does that ring some bells? Do you recognize that process? Called L'Hopital's rule. Let's do it with a trig function then. The limit as t tends to infinity of the sine of 1 over t over 1 over t. Now that's a little bit weird, kind of unusual looking. Let me tell you what it started life off as. It would probably have been that guy when it started. But you can't do L'Hopital's rule with products. Don't you need a fraction to do L'Hopital's rule? So what we did is we took that t and kind of artificially created a fraction by putting it on the bottom but calling it 1 over t. So isn't mathematically this and this the same guy? Now, L'Hopital's rule kicks in. Differentiate the sine of 1 over t. Well, make sure that we're aware that it's a chain rule. It's the cosine of 1 over t times the derivative of 1 over t which is 1 over t squared. Right, so if you differentiate sine of 1 over t, you get cosine of 1 over t times the derivative of 1 over t. And on the bottom, you differentiate 1 over t, which gets you that guy. And something really nice happened. These two cancel out, and we now have the limit as t tends to infinity of just that guy. And now we can plug in infinity. But the cosine of 1 over infinity, we saw a few minutes ago, is the same thing as the cosine of 0, which means the answer is 1. So the limit of t sine 1 over t is in fact a number, it's 1. Any questions so far? Are we feeling good? Do another L'Hopital then. Which one should I try? Hard to think of good ones. No, I've done that one. Okay, that'll have to do. Try to think of a better one, but that's the only thing that came into my head, so I'll use it. The limit as t tends to infinity. According to L'Hopital, you differentiate the top and you differentiate the bottom. In this particular case, the 3's cancel. And then I just do L'Hopital again. And I get 2t over ET. But if I plug infinity in, I still get infinity over infinity. So I do L'Hopital a third and final time. Only this time, I can do the brute force part and get 0. When you do L'Hopital, isn't it likely that you're going to do it more than once? You may have to do it 2 or even 3 times before you get your final answer, right? The destination, in this case, 0. Are we good? Right. I'm going to finish with, give you some weird calculations that could have happened in brute force. Suppose you get 0 over infinity. Suppose that happened. What is 0 over infinity going to get you?
Would it just be 0?
No, but I understand. Oh, rewind up. Yes. I said no, but I talked to myself out the answer. Why is that 0?
Because
You're right,
you
it
can
is.
take any number and you can take 0 and divide it by any number in the world and it'll still just be 0.
Right. As long as the top number's not infinity, you got 0. My brain was thinking of that one when I said no to you the first time. Infinity on the top, 0 on the bottom. What would that get you?
Is it undefined?
Technically, yes. And it's undefined because?
You can't divide by 0?
Yeah, or you could just say that it's infinite.
Oh.
Would you agree taking infinity and dividing it by 0 just makes it even more infinite? And hence it's undefined. But we tend to use the word divergent now. So things converge to a number. So you say converge to 0, or you say diverge. you know, if it's not a number. I think that's the most obvious. Oh no, I guess there's, no, that's, oh no, no, you can't. Infinity over infinity or 0 over 0. If you ever see either of those two, I want you to think the hospital. These are the two major, what are called indeterminate form. And what you would do is you differentiate top and bottom, and hopefully some situation would appear where you could actually brute force the final answer. And that is perfect timing. So